Hello, my name is Adrian Kelly from EPRI, and I'm here today to talk to you about the L2RPN competition for ICAPS 2021. So L2RPN aims to effect control in a network control center. As you can see on the picture on the left, this is a typical control center in a country or region anywhere in the world. You've got multiple people working on multiple desks with multiple screens and a large video wall display showing the entire network. The aim that the people have is to control or optimize the network to make sure that power is served to customers at all times and power is restored if there are disturbances on the network, such as lightning strike, fires, vandalisms, storms. As you all know, decarbonization, decentralization, digitalization are changing the way electricity networks are being operated today. In the 20th century, electricity was perhaps the most advanced man-made achievement. What we want to ask for L2RPN is, will AI be the 21st century's most advanced achievements? And to quote Andrew Ng, artificial intelligence is the new electricity. With L2RPN, we aim to see if these two increasingly emerging areas can be merged in the form of a challenge to help solve the climate issues that we face today and in the future. So that sets the context. Let's start by preemptively answering some questions that we typically get on L2RPN. So I showed a picture of the grid control center in the last slide, but the intention here is very much not to replace the people that operate on the system. In a similar way to autonomous vehicles, not replacing actual drivers. We think of the L2RPN project as being focused on creating an autopilot for the system. Typically, systems now are very, very difficult, if not impossible, to manually control every single element. So there is a certain amount of automation there now, but systems are becoming more complex as renewable energy penetrates and as demand starts to shift on the network. What we aim to do here is not replace the human operators, but to have an agent or decision support to guide their operator, something that has advanced foresight, that can flag issues to the operator and solve them in very rapid timeframes. One of the second things to note is that this is many, many ways years away from production environments. So real-time operations depend on critical systems, monitoring the systems second by second. So this is early stage, but we have made some progress in the last few years through competitions, but it is an extremely complex challenge and problem, but it is some years away from production environments. Our aim is to start small on synthetic test networks and keep building and building and building and scaling the issue as we set new challenges for competition participants. Now, finally to note is this is a critical challenge for the future of the energy system and the future of the planet. Optimizing this increasingly complex network will bring in numerous benefits, not just cost, but it will allow more renewable energies to get on the system, and it will restore networks rapidly whenever they face challenges from storms, fires, or other environmental events. Let me start by introducing the team, the collaborators of this project. This is a joint collaboration between RTE, the French transmission system operator, led by Anton Marot, Benjamin Donneau, and Karim Chawak. RTE collaborated with EPRI, so myself, Adrian Kelly, and Dexter Lewis and Pratik Kulkarni. And this year we're also joined by PNNL, Pacific Northwest National Labs in the US, by Juhao Guang, and by TU Delft by Joshua Bremer. Ramji Hossain from Iowa State has also provided invaluable support. This is a collaborative project team. We meet regularly to set the parameters and set the competition, and we're grateful for everybody that has come involved and joined in any way. Once we build the team, the second thing is we try to engage the communities. So typically the power system community is on one side of a wall, and the AI machine learning reinforcement learning community is on the other side of the wall. Power system community engineers are typically honed and look to solve problems the way they always have, and tend not to look outside the industry or look towards the AI machine learning community. On the other side of the wall, AI experts and scientists may not be engaged or aware of the challenges and how their techniques and expertise and knowledge can be brought to bear on power system challenges. So what we aim to do with L2RPN is to bring these two communities together. We released a white paper describing reinforcement learning for electricity network operation, which was a description of reinforcement learning for engineers and engineering for reinforcement learning people. So yeah, the aim out of the gate is to break down these barriers, bring these two communities together, and grow the community of problem solvers in grid operations and power systems. So the third thing is to define the challenge. I spoke about network operation having an agent in the control center guiding decision making, but you might be wondering what exactly an agent can do. What do the people do when they're in the control center sitting there operating the grid? So what we wanted to do was to see, was there flexibility in the system? So typically a network is made up of lines interconnecting cities and towns. Lines interconnect generation sources, so power plants, wind farms, solar farms, and demand or load, which is people switching on lights or industry, heavy industry or commercial activity in towns and cities. So a network is made up of generation, creating power, feeding power to domestic consumers or demand right across countries, states, regions, and continents. These lines are interconnected and they can be rearranged. So a line can be switched out or disconnected, and power flows much like water in a pipe network. If a line is disconnected, water still needs to get to its sink source. So power still needs to get to the demand whenever people switch on light switches, TVs, and Wi-Fi. So this grid topology can be rearranged. There is some flexibility in it to reroute power around the network in different areas to be most optimal or most efficient with the network in use. We also see this grid topology isn't static, so it's constantly being kind of built and added to. This has become a little bit of a challenge in the Western world due to problems with planning consents and large infrastructures. While grids have expanded, they're also expanding at a slower rate. So grid operators have to get more flexibility out of the existing topology that they have. And typically in control centers now, there's tools used to study contingent events, but the tools are not very advanced. So you have to do one action at a time or a couple of actions at a time and look and see what the results are. You have to manually process these results, manually carry out these studies, and it's usually based on experience or previous mental models of how problems have been solved. These grid topology arrangements are inexpensive, so they don't cost too much to rearrange the network to switch out the line, switch out a line or switch in a line, but you cannot instantaneously draw a line from a node to a node. So if you look on the slide here, this is the network as is. So to get from this node on the left to this node on the right, it's not possible to develop a line instantaneously. You have to route power around the two different ways here. This is showing how a topology can be split. So if you can interconnect these two red nodes, you have almost a square, whereas when you split them, you have two separate triangles that are linked via this node here. So there is a lot of flexibility in these actions, but the action space swells once you get beyond 5, 10 nodes. You have hundreds of millions of combinations that can possibly be connected. The power system devices are changing as well. This is an example of a device on the network, and it has a control mechanism or control system. So lots of the devices on the network can be controlled by the control center. So changing set points to limit or push more power around the network. So there's more flexibility in that way because there's better devices and better control of devices that are there. These devices, again, inexpensive to do. There's no major cost with controlling devices in this way, but right now they're not too widespread, only on very advanced grids are these controllable kind of power flow routing devices. Lastly, the load or the generation on the system, that has also an amount of flexibility on the network. So you can change the generation patterns up or down. You can't generally change demand up or down. Generally, you want to reduce demand. And that's not always possible because everybody likes a certain reliable electricity supply. But generation can be shifted, so it can be reduced in one area, increased in another area, but this can be expensive. You may have a situation where you have a very expensive plant on this at this part of the network and an inexpensive plant on this part of the network, but to serve load at this red node, you have to increase the generation at the expensive plant and reduce the generation at the inexpensive plant. This adds costs onto network, which eventually adds to electricity bills, utility bills. So essentially what we want to do with L2RPN is to look at this network and explore it to see, is there hidden flexibilities within the network? Is there underexploited grid topology changes we can make, system device changes, or increasing or decreasing of the generation load balance? So our objectives with the L2RPN challenge for the last few years are to democratize the organization of competitions. We see competitions and challenges as being a really effective way to drive innovation in this field. We're able to engage with experts worldwide. We have participants from Asia, North America, Europe, to get involved and try to solve this problem and work together, collaborate, educate each other, and open source code at the end of the competition. So we want to democratize it and make it open to absolutely everybody to compete with. All you need, it's free to enter. All you need is some computing, some compute, and some knowledge and some strategy to develop to participate in L2RPN. We want to educate the machine learning community about the challenges with grid operation and vice versa. We want to set the competitions as playgrounds or training programs so that new collaborators, students, and new teams can come and join. We want to demonstrate that competitions can be created rapidly. We want to increase the speed of competition development. We've developed 3 to 4 over the last few years, but we want to do 3 to 4 per year, increase the speed and rapidity for increasing the complexity and the challenge. And we want to keep this competition dynamic going. We want to attract the largest possible community, and we want to get publicity for what we're doing to make sure that everybody knows about what we're doing, so that we can get more participants, more people contributing to it. I have some links, so when you get the slides, you can click directly on them. I'll explain the dynamic of the tracks as I go, but you can click directly here to get to Coda Lab to participate in the competition on these blue boxes. These are throughout all of the slides. So we wanted to gamify the problem of network operation. So taking our steer from Google DeepMind learning Atari, we wanted to see and see could that be applied in the framework of network operation. So in 2019, the team in RTE developed a small test case 14 node system, as you can see at the top. With an environment and a GUI like this that you could operate the system. You can see some overloads on the system here on the right, and reaching game over when you have enough lines disconnected or load and generation disconnected. And then on to 2020 last year and into 2021, we scaled this, so went from 14 bus system up to 40 buses or 118 buses, so a larger grid, more resources on the system, more nodes, more lines, more resources, bigger challenges, and bigger issues. So definitely an evolution from using reinforcement learning to solve the problem of grid operation in real time. A larger image of the initial competition, 14 bus competition. So let me now give you some context on the overview of the challenge and how the environment is designed here. We want to cast the problem of grid operation as a typical Markov decision-making process. So agent, environment, action state, reward, and costs. So the environment here, if you look at this classical depiction, the environment is the grid, the network, the what ties together your electricity system. The observations that you get from the environment are going to be flows on the lines, generation sources, again, from nuclear, wind, coal, gas, hydro. Demand means electricity that's used by you and I as we switch on lights and switch on kettles and coffee makers. The topology of the network, which is how the grid is interconnected. So line from A to B, to C to D, from E to F. We also have an observation of a month, a day per year. So this is a time series problem across 5-minute time intervals. So you need to know at what stage you're at during the day. Is it morning, nighttime, evening, have different demand patterns, for example. I should say that one of the issues with electricity networks more generally is that generation and demand have to always meet on the system. So if you have a demand of 1,000 megawatts, if there's 1,000 megawatts being used by all consumers on a network, then there has to be 1,000 megawatts of generation at all times. If there is a mismatch, the system becomes unstable and will collapse. So second to second, there's always a match in generation meeting demand. There is some element of storage with battery storage, but that's early stage in development. But think of it as a constant balance. The action from the agent in the environment showing here. So the agent can take actions on the environment, so that can be to disconnect or reconnect transmission lines, change the topology of the grid, change the generation on the system, not quite at changing demand. We don't want to change demand, like I say, but agents can take observations and act on the environment to change the state. The state then is the status of the grid post-action, naturally, and then the reward, which is negative cost. We penalize lines that are overloaded. So lines have limits, so you can only squeeze a certain amount of power down a line at any particular time. If the line gets overloaded for more than a couple of time steps, then that line will disconnect itself from the network. It'll take itself out. So you will have to route power in a different direction if you lose a line. And almost like a Jenga puzzle, you can't take out more than a few lines on a network at any one time, or else it will just become unstable and start to break apart into smaller islands, and the system becomes unsolvable, which leads to a blackout, an electricity blackout in reality, or in the context of L2RPN, a game over condition. So what we aim to do is get participants to develop agents to control the grid over multi-day periods, maximizing the reward or minimizing the costs on the network. And game over arise if you have too many overloaded lines across multiple time steps, or if you disconnect electricity loads at different buses. If you look here is an example of how this can be manifested with a very simple example. On the right hand side, so this is a simple 4-bus system with 5 lines. So A and D are connected, and then it's connected in a square environment. So you can see here the red line indicates an overload. There's too much electricity power getting generated on this line, flowing down this line. So if that is greater than 2 seconds, this will disconnect itself entirely. So what the agent does is takes the observation of the overloaded line, and it acts to split this node in the corner here. So by doing that, it reroutes a certain amount of power through the line across the middle and reduces the power that's on this line here. So with a simple splitting action in the substation node here, you have all of the load is served perfectly, and the overload has disappeared from the system. This is a simple example of what operators do in real time and what we expect the agents in L2RPN to carry out. So when the RTE team designed the game, what they wanted was a realistic, interesting, and feasible representation. So realistic being, although it is a synthetic network, it's not a particular country or state. It's a synthetic network. We want to represent real-world characteristics. So the generation, the energy mix is realistic. There's renewable energy with nuclear energy and thermal energy and hydro energy. So this is a realistic depiction of what's happening now. The loads, demands are all realistic as well. The capacities of the lines are realistic and based on physical characteristics. So in reality, you can live with an overload for a certain amount of time. If there's too much power going down a line on a network, you can live with that. So it represents the physical characteristics of this. It will only disconnect after 2 time steps. We wanted to make sure that we have an interesting game or interesting challenge. So there's diverse actions. You can redispatch load or generation, or you can change the topology of the grid. You can have simultaneous actions, but you cannot act very rapidly. There are cool down periods for disconnecting lines. This is feeding back into the realistic elements of the competition. There's time budgets associated with each action, and agents are tested on blind scenarios, and they're tested against an agent that would do nothing in a scenario. So we wanted to make sure that the competition is interesting, and the actions that the agent operator can take are also interesting. We also want it to be feasible. There are solutions out there that do avoid game overs when we test them. So we don't want to throw infeasible, unsolvable, intractable problems at them. We want to use small synthetic grids rather than very, very large complex grids to solve, but we will scale that problem out as we go, whereas larger grids have a wider variety of actions and solutions, and it tends to increase the action space. So we wanted to make these realistic, interesting, and feasible, and this is what goes into competition design and environment design. So let's finally talk about the L2RPN series. So we started in 2019 with a small grid, like I showed, that black background. In spring of 2020, we launched the IJCNN feasibility challenges. So this was with a small area of a large grid, so a medium-sized grid. There was maintenance on this line, on this network. So lines and stations were being taken out of service occasionally. So that was changing the topology kind of randomly, or not quite randomly. There was some planned on it, but it was weakening the network by taking lines out. Again, back to the Jenga puzzle, and the agent had to solve and keep balance here, even with maintenance scenarios. In 2020, we launched the NeurIPS Sustainable World Challenge, or entered this NeurIPS Sustainable World Challenge. So throughout that year, we developed this competition that presented at NeurIPS last December. There was 2 tracks to this, a robustness track and adaptability track. The robustness track was, again, a small part of a large network, but it was an adversarial attacker. So a random sequence of lines were being disconnected, and the agent had to act to keep flows and in line, and to keep balance on the network while under attack. The adaptability had a larger grid, so you had the full grid here with lots of renewables or lots of thermal, different kind of scenarios for different, but allowing the full use, but with no attack. No adversarial attack. So people could enter either of the tracks. We had 2 different competitions, two really healthy competitions, some great winners, great algorithms proposed. So this year we want to talk about what are the new problems, what are the new collaborators we can work with, what are the new participants. So for 2021, we'd introduced the ICAPS challenge, which we kind of labeling the L2RPN with trust, an augmented intelligence challenge. So what we want to do is deal the agents. Again, we're scaling from 2020. We want to have agents dealing with higher penetrations of renewable energy. So there's more renewable energy on the system than there was in the systems of last year. This means there's more variability, there's more resources dotted around the network. We want to task design teams with the development of trustworthy agents. So agents to build trust between a digital assistant agent with the human operator in the grid. The agent has to communicate with that human operator to flag when they are in trouble and to flag when the grid might fail if there's a problem with it. This will build confidence and allows the human operator to come and see can they solve a problem with more tactile approaches. We want to have a zonal or locational based attention. So you can see here the grid can be quite large. We've split it into 3, east, west, and central. So if the agent sees that there's trouble, we've tasked participants to flag and tell us where on the network the trouble is. So this directs operators' attention to particular areas of the network so that they can solve the problem more quickly. So in this scenario, an agent might say, I've got a problem in the west. So the agent just has to focus on the west area to try to solve the problem. They don't have to focus on the east or the central to figure out what's going on. We're running 2 tracks, so we want to make this collaborative. So there's a track for new entrants and there's a tracks for open to anybody. And there's a student team prizes also to encourage student academic university team development. The question continually is asked so our question we always get asked in L2RPN and autonomous drivers, how to build trust between the human and the machine, the AI agent and the person sitting at the desk. So one way we like to think about this is to not to assume that there's going to be perfect operation. So autopilot isn't perfect and an agent won't be perfect either because it's the complexity of the task is too vast. So instead of that, we want to flip it around and say, can you give us confidence? Can you alarm and say when you're in trouble, or tell us what your confidence level is? So in this way, we want the agent to decide if there's a blackout on its way. They need to be able to flag this, that there's some trouble, and they need to flag in an ideal kind of amount of time. So if there's a game over scenario on its way, they need to tell the operator around about 30-35 minutes before the game over is likely to happen, because the operator can then has enough time to act. There's no point in saying the grid is going to fail a minute before it fails, because the operator cannot act. And this view fits in well. We can set this up in the RL framework. There's an operator attention budget. We don't want to overexert the operators by continually saying, I'm in trouble, I'm in trouble, I'm in trouble. They need to be optimal use of that time and attention for the operator. So it needs to be efficiently carried out. And we want to minimize out of the loop effect as well. So we want to efficiently direct the operator's attention to the issue. So it's no point in saying I'm in trouble without telling them where they're in trouble, what the trouble might be, how far away from trouble that the agent is. What are the conditions of the game? So conditions are reached, as I explained, when electricity demand is not met, if one power plant is disconnected from the network, or if the network splits into multiple smaller networks and becomes unsolvable. The conditions for overloads are overloads on lines can be if they're overloaded for greater than 2 steps, they will likely get disconnected, or if there's a hard overloading greater than 200% of its line, it gets disconnected immediately. And then if there's too many line disconnections, back to Jenga, you will have a cascade and your network will fall over and it will be game over. And as I explained earlier, the agents can act by disconnecting or reconnecting a power line, changing the grid topology, changing the generation at nodes, or reducing renewable generation. Agents are evaluated once they're submitted, so they can be tested on baselines on the network. Then the competition evaluators test them on 24 blind weekly never before seen scenarios across a year. So you have a winter case, a summer case, autumn. So you have so the agent is exposed to multiple parameters across the network. The score is your cost of operations, which gets you 70% of the way, and the attention score, which is 30% of the way. If the agent finishes, they get a maximum of 200 points, but if the agent does not complete, or if there is a game over, it needs to alarm to tell the operator there's a problem. I've explained this, so 35 minutes before failure is optimal. If there's no successful alarm sent and there is a game over, then you get penalized 200 points. And there's an alarm budget. You cannot send spurious regular alarms. And also alarms should show the location of where the issue is going to be on the network. The cost of operations is equal to the cost of the losses plus cost of redispatching, and then the total score is cost of operations plus cost of blackout. And you can learn more if you go to the competitions. Just search L2RPN on Codalab and you will find the details there. For prizes in 2021, we have a fund of $13,500 as of now. Could increase in the coming weeks and months. We're still looking for some participants, for sponsors, but €8,500 dedicated to the Anyone League, open to Anyone League, and 4,500 to the new Entrance League. And there's a $1,000 student prize on the competition. From either of the competitions. So good prize funds split across 1, 2, 3, and there's more details on Codalab. So lastly, just to wrap up, I'd just like to invite you to search for L2RPN on codalab.org. The links are here in the slide deck. We're past the warm-up phase, so we're in the development phase right now, and the test phase starts in the 22nd of September. So we have around about 6 weeks to go. So there's plenty of time. There's lots of information on the network, on the competition. So please go there. We have a Discord channel, discord.org, and the link is here. If you just search for L2RPN on Discord, you will find a very active community and participations there. Thank you for your time. I look forward to some questions, and there's some further details in the slide deck. And I would invite everybody, please come and join us. There's difficult challenges to solve. We need new approaches. We need to develop and integrate power systems engineers teams with machine learning expertise. So please consider to join us or spread the word and let people know about L2RPN. Thank you.